Right, today we are going to talk about the estimation, okay, and we will use one session to hopefully cover all this. If not, then we will continue next week, okay. So first, let's see the estimation. So what is the estimation? Estimation means that actually it is an inverse problem. The inverse problem for recovering or find out the parameter of a distribution based on the samples. Based on those samples, then we need to observe the parameter. Remember that for our common distribution, the PDF, we have the parameters like Bernoulli distribution, or geometric distribution, Gaussian, or even exponential. We always have the parameter, and we try to estimate that parameter. So if we have the theta, the parameter, then we can get our PDF, the distribution. So this is a distribution. And then for these distributions, then we have the samples. So for the sample x1, x2 to xn, those are the samples. Once we have our parameter, we can get our distribution. But now if I have samples, we go the backward, so the inverse. Only we get the samples, then we want to guess our parameter. So here it is called the estimation. To estimate the data. Then you may ask, what are the parameters? We say that actually all the PDFs have the parameters. Let's see some examples. If the random variable x is a Bernoulli random variable, then what is the PMF? The PMF, we say that the PMF has the parameter theta. Our PMF is theta to the xn times 1 minus theta to the 1 minus xn. So if xn is 1, then the PMF is theta. If the realization is xn is 0, then we have 1 minus theta. This theta is the parameter. And this theta is just like the probability in this example for Bernoulli random variable. This is the discrete case. For the continuous case, see the Gaussian random variable. We also have the parameter. And you can see that the Gaussian PDF here. Then the parameter theta is the mean and the variance. So here, this theta is mean, mu, and the variance, sigma. So if we have this parameter, we can get our distribution. And for the distribution, we have samples. And suppose we only have samples, Then we want to estimate. We know the distribution, and we want to estimate your mean, your mean, and your variance. This parameter. Then this is called the estimation. So all PDFs have parameters that will estimate. We can estimate them from the observed random variables. And this is a well-defined inverse problem. Now, we will learn 3 different estimations, but before that, we will learn the 3 elementary distributions. The first is called likelihood. So likelihood is a conditional PDF of X given the parameter theta. And then the theta is also a random variable. Then we also know what is prior. The prior is the PDF of the theta, the parameter. And then posterior. For the posterior, it is a conditional PDF of theta. Likelihood there will be the conditional PDF of X. Posterior, the conditional PDF of theta given the data X. Okay, so now, based on those ideas, we will talk about this later. First, we would like to know what maximum likelihood estimation is. So what is the maximum likelihood estimation? Suppose we have a random variable X, and then we have the PDF. For this PDF, we suppose to observe n realizations. So we have x1, x2 to xn. Those are the outcomes. Then we want to estimate this parameter. So here you can see that this is not the conditional PDF, okay, because it is just a PDF of X. But a lot of textbooks just write like this. It should be f of x, and they use the semicolon data. For example, like we may estimate the arrival rate or measure the inter-arrival time of passengers in the airport. And those we may use the maximum likelihood estimation. Let's see here. I considered a random vector x, so from x1 to xn, and then their joint distribution. So here's a joint distribution. You can also, again, at this you can also write as f of x and x semicolon theta. Theta here is a deterministic parameter, so it is not a conditional density because theta is not random. And then we assume that this random vector x, those x are ID. And if they are ID, then what is their joint distribution? For their joint distribution, they can separate that to have a multiplication of each PDF. And here again, this is not the conditional PDF. This is just that theta is just a parameter. You can put that column, semicolon. Okay, so overall, it is a multiplication. So for this multiplication, and this is ID, so later on you can just choose either one because they are identical. How do I find the theta to maximize this density? So to find the best theta, then we can maximize this above density. Okay, remember that this is still a PDF, so this might be the PDF. So which theta can maximize this density? we want to find the best theta, so we can to find the best theta. Okay, we need to find the inverse, the arc max of this, and this theta is just the maximum likelihood theta, and this is the maximum likelihood estimation problem. So to find the best theta in equation 1, what should we do? First, we can take the log. So if I take the log, after I've taken the log on both sides, the left-hand side is log x1 to xn, x1 to xn, and we have theta. We just put that semicolon. Okay. If I take the log from the right hand side, log AB will be what? Log A plus log B. Right. So the right hand side is the summation. The multiplication becomes the summation. N from 1 to capital N. Log f of x on x n of theta. Why we can take the log? Because log is monotonically increasing. So to find the maximum, the maximum will be still preserved. So we can take the log. Here is the example. We observe a Gaussian random variable, and we know the variance, but we don't know the mean. So the mean now is theta. And we have n observations from x1 to xn. Then we want to estimate this unknown mean theta. So this is our Gaussian distribution, right? We know this. We know everything except this data. Then we try to find this data, and to get this data, we will get the maximum of this PDF. So the goal is to estimate the data. Now we have n observations. Let's just reduce that to simplify it. First, we just have one observation, and then later on we have 2 observations, 3 observations, and then goes to the general n observations. So if observation is 1 and only have 1 data, then to find this best data, okay, we maximize this PDF. To maximize this PDF, you can see that how do I maximize this PDF? This is the same. So we need to maximize this part. This is exponential. Suppose it is exponential data. Then I want to maximize this data. Okay. And since this data is e to the minus x minus theta squared, so I have a minus sign. That means I just need to minimize this part. Or you can still maximize. This is like maximize minus x minus theta squared. That will be equal to minimize the square term, because I have a minus sign and max to mix. That means the minimum. Okay, so to find the minimum of this perfect square, so what is theta? So to minimize that, this is 0. If the theta is 0, that means the mean is 0, then I get x1. The minimum for this perfect square, that'll be x1 when we get the theta equals 0. Yeah, because this like this shape. So that means my theta should be equal to x1. So the best Gaussian that fits this observation is the x1. The mean is x1. So we can have a plot. I have a Gaussian, and then here we have x1. That is in the peak. Okay, this is just for one observation. If I have two observations, let's see. If I have two observations, I have x1 and x2. And for x1 and x2, I need to maximize this multiplication because they are ID. For the first PDF here, a second Gaussian, so I can combine these two. To combine these two PDF, we have this perfect square, and then for the exponential, the exponent, the power is in this expression, minus theta 1 minus theta, x1 minus theta square, and also x2 minus theta square. To maximize this part, okay, we can skip this square. So we need to maximize this power, this exponent. Since we have minus sign, so that means we can find the minimum of these two perfect square. And to find the minimum, how do we find the minimum? We take the derivative. Okay, 2x1 minus theta plus 2x2 minus theta equals 0. So theta is x1 plus x2 divided by 2. Okay. So if I have two observations, then the best mean is just also the mean of these two observations. So the best Gaussian that fits x is x1 and also x2 is the mean x1 plus x2 over 2. If you plot, this is x, and we have a PDF Gaussian, then my x1 and x2 should be here, x1 and x2. And then their mean will be on the top. Okay, now we can go to the general n. If I have n observations, for n observations, then I have because they are all Gaussian. So here I have this term to the n, and we don't need this later on. Okay, and then exponential. We do exponential something, exponential something, exponential something. So for this exponent, I do a summation. Then to find the best theta, we can take the log on both sides. So if I take log left-hand side here, and also the log for the right-hand side. Again, that I have A and B. So if I take a log, so I have a log A and then log B. And then log A to the n will be n times log n. N times log A. Now, to find the best theta, we can take the derivative. So to take the derivative, log n from 1 to capital N f xn So we don't need to care about this log term. There's no theta here. Second one, the second term, this will be the summation n from 1 to capital N, xn minus theta divided by sigma squared. And they should be 0. So that gives us the best theta is 1 over n summation n from 1 to capital N xn. Then the maximum likelihood estimation for this Gaussian is this one. So therefore, the maximum likelihood estimation MLE is 1 over n. Also take the average of your observation. Okay, so now the MLE, this best theta is also the average of your observation. So here's a note. For the best in the maximum likelihood estimation means that the parameter can maximize the probability density for a particular observation, x equals x1 or x equals x1 to xn. So let's maximize the probability density function. This best theta is also the empirical average of the measurement. And you see that this is the average of your observations. Okay, let's see another example. This is the example for continuous case. Next one is the discrete case. x1 to xn are IID, and IID Bernoulli random variable. For their parameter, theta is when xn is 1. If x is 1, the observation is 1, then the probability is theta. And we observed n observations. So first, we can write it down. The PMF of xn, this is theta. When xn, this observation is 1. Otherwise, it is 1 over 1 minus theta when the observation is 0. Remember that for the Bernoulli random variable is either on and off, heads or tail, or like 1 or 0. So overall, we can say that this PMF xn with the parameter theta is either theta to the xn times or 1 minus theta to the 1 minus xn. So they time together. So this is just for one observation. If I have the joint PMF, for the joint PMF, I have x1 to xn. Then that'll be the product. Okay, n from 1 to capital N. Theta to the xn, 1 minus theta to the 1 minus xn. So to find the best theta, we need to take the log. Here we can still take the log because after taking the log, we still preserve the maximum. So taking the log. So I have a log. Here we just write the vector x theta. So the product becomes the summation. So I have xn log theta. That's the first term. Second term, this part, that'll be 1 minus xn times 1 minus theta, log 1 minus theta. 1 minus xn times log 1 minus theta. Now to find the best theta, we need to take the derivative with respect to theta. So taking the derivative with respect to theta. So d theta. On the right hand side, we have one minus xn times log 1 minus theta. And it should be 0. So we have n, the summation n from 1 to capital N, xn over theta minus 1 minus xn over 1 minus theta. This overall will be 0. Then what is the theta? So the best theta is 1 over n, or again, the average. Let's see another example. Theta is unknown. And then we have a random variable w, that is the Gaussian, with 0 mean and variance squared. And it is I the Gaussian noise. And we have another random variable y, that is the unknown scatter theta plus this Gaussian noise. And we observed y from y1 to yn. So we need to figure out the best theta here. We can write it down the PDF of y, because w is Gaussian and this is just a scalar, deterministic scalar. So y definitely is a Gaussian, right? And since wn is 0 mean, and now I plus theta, so the mean for y will be theta. And then we try to find this theta. Okay? So first, the joint PDF y1 to yn y1 to yn with theta, it should be multiplication of your Gaussian n from 1 to capital N. 1 over square root of 2 pi sigma squared. Those are all known. The only unknown is the mean. So it is here. I have 1 over square root of 2 pi sigma squared n times. So this to the n, capital N. And then exponential, we have the summation minus summation n from 1 to capital N. Yn minus theta squared over 2 sigma squared. Now we want to find the best theta. So the best theta is to maximize the theta for this joint PDF. Why? We want to maximize this. So here we don't need that. We only need to maximize this part. So arc view. The negative summation. Right, to find the maximum of this summation, we need to take the derivative. To take the derivative, we have 2 times summation n from 1 to capital N Yn minus theta. This should be 0. And then we can get our maximum likelihood theta, the best theta. Again, that's the average. Okay. Now suppose we have another random variable called m. Okay, for this random variable, that is the average of your random variable y. Then I want to find the moment generator of this random variable m. So remember that what is the moment generating function? By the definition, that is the expectation of e to the s times the random variable. And since the random variable is the average of another random variable y, so we can get e to the s 1 over n y1 plus y2 to yn. And that is the expectation of e to the s over n times y n overall to the n because they are ID. And now remember that for the moment generating function for the Gaussian, the moment generating function of Gaussian is e to the theta s plus sigma squared s squared over 2. So here, this should be e to the theta, s becomes s over n. Sigma squared s becomes s over n squared over 2. Overall to the power n. So we get e to the theta s plus sigma squared over n times s squared over 2. Right, so now let's see these two terms, estimate and also the estimator. So what is the estimate? Estimate is a number. Estimator is a random variable. So for the estimate, it is a number. For example, like our best theta for maximum likelihood estimation will be 1 over n summation or just the average. It is the estimate. So estimate is a random realization of a random variable. But an estimator is a random variable. Okay, we can write it down. Theta, this is a random variable. So it takes a set of random variables and then generate another random variable. So I have a random variable x, and I take the average. And we'll say this is another random variable. This is an estimator. Okay, so estimate is a number. Estimator is a random variable. Then you probably have heard that for estimator, I have biased estimator and unbiased estimator. So first, let's see what is unbiased estimator. We say the estimator theta is unbiased if the expectation or the mean of this estimator is your estimate or the true parameter. So the average of the random variable matches the true parameter. For example, I have the ID Gaussian random variables and I have unknown mean. So the mean is theta. So we can get the maximum likelihood estimator. Is oh no. This is the average of your Gaussian random variable x. And let's say something here. The average of a random variable matches the true parameter. That means that we allowed this random variable to fluctuate. And then we expect the average will match to the true parameter theta. Expect the average to match the true theta. So for the ID Gaussian, the maximum likelihood estimator is here. And then we expect, hopefully, that the mean or the expectation is 1 over n. N from 1 to capital N, expectation xn. This should be 1 over n summation n from 1 to capital N theta. And this is theta. Just match the true parameter. So we will say that the maximum likelihood estimator is an unbiased estimator. Of theta. Now another example, if my theta, this random variable is x1 plus x2 plus 5. Now let's find the mean. The mean is expectation x1 plus x2 plus 5. This will be x1 plus x2 plus 5. I think it's better to have a note because we still think that x is the Gaussian, ID Gaussian. Okay, so suppose this is the note. Then this we have 2 theta plus 5. And then this is not equal to theta. So this estimator is biased. Next example, I have x1 to xn ID Gaussian random variables, and we don't know the mean, and also we don't know the variance. Then our maximum likelihood estimator are for the mean, that's 1 over n, n from 1 to capital N, xn. And then for the variance, sigma square, that'd be 1 over n summation xn minus the mean. Now for simplicity, that we assume that the mean is 0. For simplicity, we assume that the mean is 0. So the second moment, expectation xn squared is equal to, because the mean is 0, That is your variance. Okay, so now let's take a look about this maximum likelihood estimator of the variance. Okay, so we will take the expectation and check if it is biased or unbiased. So first, let's take the expectation of your maximum likelihood estimator of your variance. So it should be 1 over n summation n from 1 to capital N. And then we take the expectation. Inside this square perfect, we have minus 2 expectation. The mean times the variable x, and then expectation, your mean square. So this is equal to, the first one is a sigma square. Now the second one, what is this estimator here? So we can bring it to this expectation. Minus 2 times expectation of 1 over n, and this is x, well, j from 1 to the n, xn. And then expectation 1 over n summation remember their ID. Okay, so the middle term, this one, I can simplify it to 1 over n expectation xj times expectation xn. And that is 0 because they are independent. This is for j is not equal to n. But we still, if j is equal to n, we still take a look about this the middle term. 1 over n summation j from 1 to capital N xj times xn. So there'll be 1 over n expectation x1 xn plus x2 xn plus x3 xn and also x4 xn, finally to x capital N times xn. So if they are not the same, j is not equal to n, this should be 0, 0, 0. Until they are the same, then I have a sigma square. So 0 plus 0, and we have so many zeros. So overall, you get sigma square over capital N. Now let's see the last term. For the last term, 1 over capital N, xn, n from 1 to capital N is overall square. This is 1 over n squared times the summation. For j is not equal to n, this expectation is 0. So they go to 0. So we only have 1 over n squared, summation n from 1 to capital N, sigma squared plus 0. So this part is sigma squared over n squared. So now we can check the expectation of this best variance is 1 over n, summation n from 1 to capital N, sigma squared minus 2 sigma squared over n plus n here plus sigma squared over n, and this is n minus 1 over n sigma squared, and it is not equal to sigma squared. Therefore, this maximum likelihood of variance is a biased estimator. And you may say that what is the unbiased estimator for this one, for the variance? So actually, the unbiased variance, unbiased, is 1 over n minus 1 This is unbiased. But here you can see that for the unbiased estimator, this does not maximize the likelihood. So it means that it doesn't mean that the unbiased is good or bias is not good. It really depends on your purpose. So this unbiased estimator does not maximize the likelihood. So now here is the summary. So an estimator is unbiased when the mean is when the mean matches the true parameter. And unbiased means that the statistical average is the true parameter. But is that good or bad? We don't know. The next one is called the Maximum-A-Posteriori, or called the MAP. We have the parameter theta, and now this data is random variable. And we also have the distribution for this parameter, f of theta. Remember that in the maximum likelihood estimation, the parameter is deterministic. But now we're talking about the parameter that is a variable, and we have the PDF. And for this PDF, it's called a prior distribution. For the maximum likelihood estimation, we try to maximize their PDF. And you can see that this X is like a vector. Okay, so it's a random vector. But for the map, we're still trying to find the parameter, and this parameter based on their conditional PDF. And we call this distribution is posteriori distribution. Let's see the difference between the maximum likelihood estimation and also the maximum posteriori. For the maximum likelihood estimation, the likelihood is deterministic. The parameter is deterministic. Here, the parameter. Data is deterministic. But for the map, the parameter is a random variable. It's a random variable. And for the maximum likelihood, we don't have a prior, so no prior, because theta is deterministic. But for the map, we have their distribution. And for the maximum likelihood estimation, we try to find the peak of the likelihood of your PDF. And then for the map, we also find a peak, but this peak is not just for the likelihood, it's for the posteriori distribution. Vector. So suppose we have a random variable x, This should be theta. Okay. So with the PDF, x given the theta now is a random variable. And I also have the PDF for the theta. And we observe the n realization, x1 to xn. And we also want to estimate the realization of theta of this random variable theta. So how do we solve the map? We can use the Bayes theory. By Bayes theory. So we try to find the theta for the theta given x. And then use the Bayes theory. What is this conditional PDF? F. Okay, two terms. Oh, I see. It should be two terms. Okay. All right. So from the Bayes theory, there'll be the conditional PDF of x given theta. And here you can see that this x is a vector, a random vector. Oh, this is a random vector. Let me see, suppose, no, just one random variable, so fine. This should be x. Okay, so by the Bayes theory, I have a conditional PDF x given theta, and then we times the prior distribution, divide by the PDF of x. And you can see that we try to find the theta, okay, to maximize this PDF. So the denominator, this term, it is independent of the maximization. So we can get rid of that. We don't need to ignore it. This part is independent of the maximization. So we only care about the numerator. This is just for one observation. If I have n observations, then we can rewrite this in a vector form. So the theta is arc next the theta f. Now it's a random vector. Then there will be a product, and because they are ID. The conditional PDF and of x given theta, xn given theta. Now suppose the prior distribution is Gaussian, and also the conditional PDF, this is also Gaussian. Okay. First, when n equals 1, if we have only one observation, then what is the data? The best data, let's see. If I have only one observation, go to this part. But if we assume that they are Gaussian, so this is the Gaussian times the Gaussian, then so this part we can also ignore. Maximize e to the minus a times e to the minus b. Then we maximize minus a minus b. Okay. So we try to maximize this. Take the derivative and set it to 0. Then you will get your theta is x plus sigma square mu divided by 1 plus mu square. And if n equals 2, when n equals 2, then we have this two part still times the prior distribution. So for these two parts, I have kind of like a coefficient terms, and we have an exponential, and also for the prior. So we only need to care about these three terms, right? To maximize these three terms. And then you'll get x1 plus x2 plus sigma square mu divided by 2 plus sigma square. Then for general n, now for general n, similarly, we don't need this part, only exponential and also the prior. So focusing on these two exponents, to maximize these exponents, then we get theta should be m plus sigma square, and then the numerator is this, the sum of your realization plus the sigma square, the variance times mu. So you can see that if my realization is less, small, then the variance take the lead. So the factor sigma square has significant influence. What does that mean? So if we have a few observations, then we will probably rely on the prior. But if n is going up, then the influence of the prior may go down. Then the next question is what kind of prior should we choose? Because here we just say that we have a prior called f of theta, and we have the distribution. And which distribution should I choose? You can base on your preference from the historical data, or you can base on the physics that the PDF should satisfy that one, abide by the physical law. Or you can choose a prior that is computationally friendlier. Okay, so computationally friendlier, what is that? First, see this example. If I have a Bernoulli distribution with a PDF, okay, here's our PDF, and I want to find a map estimate. Okay, this is the map estimate. Then we assume there's a prior. Okay, but what is that distribution? We don't know. Just assume we have a prior. So you do the you try to find the theta. Here is your final form. You try to maximize this, and then you see that we have our prior here. So suppose first, let's see if we assume that the prior is Gaussian. So this is Gaussian. The Gaussian prior. Then what happens to this one? If I take the log, then I only need to care about the exponent. So the map becomes still the same thing here. Okay, so we have xn log theta plus 1 minus xn log 1 minus theta. And minus, here we have theta minus mu squared divided by 2 sigma squared. Now we can take the derivative. And then also set it to 0. We have the sum of your realization divided by theta. And n minus the sum of your realizations divided by 1 minus theta. Then it should be theta minus mu divided by sigma squared. Now with that, this summation is just S. Okay. That S equals the summation. Then we have 1 minus theta sigma square S minus theta sigma square n minus S. That's theta 1 minus theta times theta minus mu. Okay, so we still can find the theta. This is the cubic polynomial problem. And we can have a closed form. Solution. But you can see that it is so tedious. So maybe this prior is not good. Then we choose another prior. The second prior, this is a Laplace prior. And then you can simplify your best theta. And then you get theta should be here minus lambda and absolute value of theta. And for this one, we cannot get a closed form solution. It is a convex optimization. And the no closed form. Solution. So maybe this is also not good. Then another one, if we consider this, this prior is called beta prior. Then you can find the best data for map. Should be n from 1 to capital N, xn log theta plus 1 minus xn log 1 minus theta. And then for our beta prior here, we have alpha minus 1 log theta plus beta minus 1 log 1 minus theta. Again, the S is for the sum of your realization. So this can be written as S plus alpha minus 1 log theta, and then n minus S plus beta minus 1 for log 1 minus theta. You can take the derivative. So taking the derivative as plus alpha minus 1 divided by theta should be equal to n minus S plus beta minus 1 divided by 1 minus theta. So you can get the data. S plus alpha minus 1 divided by n plus beta plus alpha minus 2. So you can see that this posterior distribution, the posterior distribution still remains in the same form as the prior. And this beta prior is a conjugate before the Bernoulli likelihood. If we choose a prior that is computationally friendlier, actually this prior is called conjugate prior. And that means computationally friendlier. That means they won't change the form of the posterior distribution. Here you can see we'll get the same form for this prior. If we times, you can see that the form is similar rather than like Laplace prior or the Gaussian prior. Hard to find out your data. The conjugate prior means that a prior, when multiplied by the likelihood to form the posterior takes the same form as the prior. And then every likelihood has its conjugate prior. And for the conjugate priors, well, it's easy to find, but they are not necessarily good priors. Okay, for the conjugate priors, it is just computationally friendly. Okay. Computationally friendly. But maybe they have a good physical interpretations. Here's a note for overall. If we have enough observations, or the observations goes to infinity, then the map estimate will be close to the maximum likelihood estimate, which means that if we have enough samples, then we trust the data. But we have less observation, then the map estimate will go to the theta naught like the prior. That means if we do not have enough or any samples, then we only trust the prior. Okay. The last one is the minimum mean square error estimator. What is this? X and Y, they are joint distributed random variables. Suppose we want to estimate the X given Y, and given Y is fixed. Then what is the best estimator of X given Y equals assigned value? So one commonly used error criteria is the square error. And in this case, we try to minimize the mean square error in our estimate given our observation. So we want to find the function to estimate X given Y, and make sure that the expectation X given Y I should be capital X. Okay, this is minimized. The error is minimized. Okay, so the function cy is to estimate X given Y, Y equals a number. And then we try to make sure that their mean square error is minimized. Let's just see the claim. The mean square error is minimized. How can I minimize the mean square error? If we let this function cy, it is just the conditional expectation X given Y. Because the error, here's the proof. If it is the conditional expectation, it should be X minus the function times their joint distribution. And then for the X, for dx, we have a joint distribution. We can rewrite that using the conditional PDF. That is, the joint PDF can be written as the Fy times the X given Y. Okay, so here the joint PDF will be the conditional PDF times the marginal PDF of Y. And what is this integration? Consider all possible function of outcomes times their corresponding weightings. Then overall, this is a function of Y. If we want to minimize this error, this error is minimized if we can pick the function cy to minimize, we only can minimize this part. To minimize the inner product, inner integral. for each value of y. So how do I minimize this inner integral? Let's see. We minimize the inner integral. Here, if I take the partial derivative for cy with respect to cy. So here we have x minus c, the function, and then the conditional PDF. And then we need to set that to 0. Then we have minus 2 and x minus cy. And then the joined PDF, the conditional PDF. Then we have two parts. If I set it to 0, the first x times this conditional PDF will be equal to the integration of the cy times this conditional PDF. So here we should have the integration x times the conditional PDF will be equal to the function times the conditional PDF. And since I'm doing the integration for dx, so I can put cy outside. So if I put cy outside, this function outside, and then I have an integration. First, what is this integration? With a PDF, any kind of PDF, if you do the integration, consider all, then this integration is 1. So we found our function. This function and this one is consider all possible outcomes times their corresponding weightings. This is the expectation and conditional expectation. So we get this cy should be conditional expectation of x given your y is some point y. And then we will use this notation. X minimum mean square error is just the expectation, the conditional expectation of x given y. And similarly, by symmetry, we can also have the y, the minimum mean square of y. There'll be the expectation of y given x. So now just see an example that you will understand this concept. I want to find the minimum mean square estimator of x given y. And here is my PMF, joint PMF. So first we can plot the PMF, the marginal PMF of x and the marginal PMF of y. Okay, so what is the marginal PMF of x? I have values at 0, 2, and 3. For 0, then my y is 1/3. When x equals 2, my y is 1/3. When x equals 3, I also get 1/3. So here is my just x. I have a value at 0, 2, and 3. 1/3, 1/3, 1/3 at 0, 2, 3. And we can also plot the PMF of y. The marginal PMF of y. My value of y is at -1, 0, and 2. And also they are all 1/3. So -1, 0, and 2. Okay, so the minimum mean square error estimator of x given y that'll be the conditional PD expectation of x given y is fixed. So which means that we need to find the conditional PMF. So first, when y equals -1, what is the conditional PMF? When y is -1, the conditional PMF is x given -1. So that's the joint PMF x and -1 divided by the PMF of y at -1. So we get 2/3, 0, and 1/3. When y equals 0, the conditional PMF of x given 0 will be the joint PMF x 0 divided by the marginal PMF of y at 0. You have 1/3, 2/3, and 0. And last one, when y equals 2. So x given y when y equals 2. Similarly, we have x2 divided by the marginal PMF of y at 2. And here we have 0, 1/3, 2/3. You can also check this. If you sum this, okay, it is still 1. So it is a valid PMF. Okay, make sure that every time you need to check, well, this should be, okay, this is 1/3, 1/3, 1/3, and you add them together, there will be also 1. Okay, to satisfy their property of the PDF. So therefore, we can find the minimum mean square error estimator. So therefore, x given y equals -1. That is the summation. Consider all possible outcomes times their weightings. Here the weighting is the marginal PMF, our conditional PMF of x given y equals -1. So you have 0 times 2/3, and then 2 times 0, and 3 times 1/3. You get 1. When y is equal to 0, then your conditional PMF, consider all possible outcomes times their corresponding weightings. That is conditional PMF with x given y equals 0. Then you get 3/4, 4/3. And for y equals 2, then your conditional expectation is 8/3. So therefore, you can say that the minimum mean square error of x, that's either (1) 4/3 or 8/3. So when y equals -1, it's 1. When y equals 0, that's 4/3. And y equals 2, that's 8/3. Okay, so now let's see that, what does that mean, that when y equals -1, y equals 0, and y equals 2, what should I expect? When y equals -1, I expect the x should be 1. When y equals 0, I expect the y should be 4/3. See, when we observe y equals -1, we want to guess what x is. And the minimum mean square estimator says that the best guess is that this minimum mean square estimator should be 1. And when y equals 0, then the best guess for x should be 4/3. You can see so first, when y equals -1, the probability of x equals 0 is 2/3, and then probability of x equals 3 is 1/3, and then you can see that the mean is 1. So it makes sense. And it is a reasonable guess. Okay. All right, the last one, just let's compare those 3 estimates. For the maximum likelihood estimate, it's the peak of your PDF. For the map, that is the peak of your conditional PDF. And for the mean square error estimator, that is the average of your conditional PDF.